I would say yet another concept from pre-calc that's hit or miss as to whether or not you really did much with it. I remember it was like a transition from I forget what they call it. It was Math 3 when I was a student. Math 3 and then pre-calc. But oh no, they didn't even call it that. It was sequential math course 3, and then it was pre-calc. But it was like I'm sure we did this. My teacher was good. It's just I wasn't much of a student at that point. So, but bless you. But she was very thorough. So I can't imagine she didn't cover it. But I do remember sitting in pre-calc with the expectation that I already knew this stuff, but I didn't. So I had to kind of figure it out on my own, which is kind of screwy. A little formatting issue here. There's a little tab issue. So something for someone. Right. So we're going to learn how to find derivatives and antiderivatives of inverse functions. So we're going to kind of discover them. But before we do that, we have to refresh our memories on inverse trig functions to begin with. So we'll start off with, just off on the side here, I'm going to draw an ordinary cosine function on 0 to 2 pi. Poor quality cosine function. Still, I mean, it's not getting any better, so I'm just going to live with it at this point. Slightly better. All right. We've talked about sine and cosine functions enough, I guess, but I will indicate the important x values and y values here. So sine and cosine functions, they have the same, for the parent functions, they have the same min and max, -1 and 1. And all the special points are the same. It start at 0, you go to pi over 2, pi, 3 pi over 2, and 2 pi. Now, those aren't the only points for which the function exists, obviously, because there's a lot of curve that exists between 0 and pi over 2, pi over 2 and pi, and so on. But those are the special ones, meaning if you know the quarter-way increments of an entire period of a function, then you know basically everything there is to know about that function, because you can just kind of backfill everything else. All right. So what we're going to do is investigate what the inverse of this would look like. So as we know, an inverse is a reflection over the line y equals x. All right, and all that means is switch the x and the y. For a graph, anyway. So I'm going to identify the coordinates along this curve specifically, even though I labeled everything. It's kind of helpful just to have stuff to point at. We have 0, 1. We have pi over 2, comma 0. And we have pi, comma -1. We have more, but that I'm just going to live in that interval for now. So that's all I'm going to focus on, just those points. So 0, 1, pi over 2, comma 0, and pi, comma -1. All right. So what I want to do is I want to switch those coordinates around. So I want, instead of 0, 1, I want 1, 0. All right, so I'm just going to jot down those important coordinates off on the side here. I want 1, 0. Instead of pi over 2, comma 0, I want 0 pi over 2. And instead of pi, comma -1, I want -1, comma pi. All right, in terms of a domain, what that's telling me for my inverse function, I'm going from -1 to 1. Right. My x values are going from -1 to 1, which makes sense because if I'm switching x with y, I'm switching all the characteristics of x with y. Right. So my x values here if I'm just focusing on this interval, it went from 0 to pi. So my y value should go from 0 to pi. My y values here went from -1 to 1, so my x values over here should go from -1 to 1. All right, so we're just doing a switcherooski on the x's and the y's. All right, so I'm going to label it up. I'm going to put a -1 here, a +1 there, 0, 0, I think that's obvious, hopefully. I'll put a pi here, and then we'll just assume that that's pi over 2 because that's half the distance. All right, and then I'll just plot some points. So -1 pi is right here, 0 pi over 2, and 1, 0. All right, so we're looking at that curve. Now, a big question that comes into play here is, all right, cool, you chose those points. Why didn't you continue beyond the pi? Why didn't you go the other way? Right? And the answer to that is actually pretty simple. Let's say I took that extra point, 3 pi over 2 comma 0. All right, 3 pi over 2 comma 0. Let me just indicate that over here. We'll do it in a different color. Let's say like a burnt orange. And it's more of a blood orange. Really some ice cream it is. If I plotted that backwards, 0, comma 3 pi over 2. Put a little question mark there. 3 pi over 2 would be about right here. 0 would be right there. So you'd be talking about this curve. It would extend further. All right. What would end up happening is you'd have something that would fail the vertical line test. All right. I would not be able to pass a vertical line through this region of the graph in such a way that it would intersect at only one location, or at most one location. All right. So what that tells me is that any value beyond what I have here is going to cause the curve to loop back upon itself and therefore fail the vertical line test. All right, so all those other points they end up being irrelevant. All right, so we don't want any of that because it's not going to be a function, and I need everything to be a function in order for this derivative stuff to work out the way it's meant to. All right, so all that stuff goes away. So none of that. And this is no good. Now again, in theory, that's stuff you already know. So hopefully I'm wasting my breath because you're like, yeah, we already know this. But if there's even one person in the room that had no idea about any of that stuff, then it's definitely a good use of time. I'm going to graph the sine function on negative pi to pi over 2, negative pi over 2 to pi over 2. So what it's going to look like, I'm just going to cut to the chase on this one. It's going to go from here to here if I just graph this piece, because I think at this point you believe me that if I graph too much of the sine function in reverse, that it's going to have an issue in terms of not passing the vertical line test. All right, so I'm going to have coordinates here, relevant coordinates of negative pi over 2, comma negative 1, 0, 0, and then pi over 2, comma positive 1. So all I'm doing is plotting those in reverse. I'm not going to make the entire table on the side. I'm just going to do it on the fly. Because the x values, the y values here become the x values. They're still going to go from negative 1 to 1. So I'm going to label up my x-axis the same way. The y values, they go from negative pi over 2 to pi over 2. So negative pi over 2 would be here. Pi over 2 would be here. And so we're just plotting away. So you're looking at something like that. All right. And so we end up with domain considerations, range considerations that come into play. Because, again, it doesn't exist for all values of x and y. So there are restrictions to things. So for example, the arc cosine function can only exist between 0 and pi, while the arc sine function can only exist between negative pi over 2 and pi over 2. And that's telling me specifically the intervals in the unit circle that make sense, right? So just kind of, I'm just going to scratch it out here a little bit. If you think back to the unit circle, the early teachings associated with the unit circle, you probably started with ASTC. And you probably did a bunch of problems associated with that. All right. What this is telling us is that the arc cosine, and you know, we could go through all the graphs for arc secant and arc cotangent and all that stuff, just to show that these go along with cosine and these go along with sine. But I think we're all at the point where we're willing to take my word for it. But what this is telling me on 0 to pi, that I'm only living in the top half of the unit circle. All right, because here's 0 and here's pi, so only in the top half. Whereas for arc sine, arc cosecant, and arc tangent, we're only living in the right-hand side. All right, negative pi over 2 to pi over 2. That's why when you do second sine, second cosine, in your calculator, sometimes you get negative values, sometimes you get positive values. It's because of that information there. If I were to find the arc, let me say the arc sine of -1/2, all right? Because it's arc sine, it's got to be in the 4th quadrant or the 1st quadrant, all right? But because it's negative, it's got to be in the 4th quadrant, all right? Because it's a negative ratio associated with sine. So it's going to tell you, I mean, when you type it in, it's going to give you something equivalent to negative pi over 6, but it's going to give it to you in decimal form. Now, if you know your unit circle values, you're just reading the unit circle backwards. So if I were to tell you the arc sine of, or ask you the arc sine of -1/2, I'm just asking you what angle in the unit circle, in the appropriate quadrants, has a sine ratio of -1/2. All right, so if you know where the y values in the unit circle are equal to -1/2, then you have it. All right, but if you don't, then you know it's a little bit more of a ride in terms of figuring out the solution. All right, but it's not over. It's just it requires more work, but it's definitely words of motivation when it comes to understanding the unit circle. Speaking of arc sine of -1/2, again, this is saying, just kind of detail it out here. It's saying what angle has a sine ratio of -1/2. All right, but it's specifically, again, on the domain, or on the interval of negative pi over 2 to pi over 2. All right, because the arc sine only exists in the interval of negative pi over 2 to pi over 2. All right, so I'm going to get a little sneaky here. Well, okay, that's like not going to be good. This is going to look terrible. I guess it's all right, but now everything's out of whack. Let me just undo. Try it this way. Well, this is the one time where I know that I couldn't just like draw it out and be all right. It's not going to work that way. Come on, you son of a gun. All right, close enough. I really got to look at the sites before I copy off of it. Unit circle, as in fill in the blank. I look at it. Stupid. All right, so if you know this information, then you're in good shape. So the sine ratio of -1/2 is where the y value is equal to -1/2. All right, but when I'm dealing with an arc sine function, I don't care about all instances. I only care about the instances in the appropriate domain, all right, or range, depending on how you think of it. So this is my interval of -π/2 to π/2. So only in this is where arc sine exists. So in that case, I'm just looking for the y value that's equal to -1/2, which would be right here, which corresponds to this angle, or this group of angles. We only work with radians. Right? Calc 3, you'll get back into degrees. But if I wrote 11π/6 as my final answer, I'm incorrect. Because 11π/6 does not fall in the interval of -π/2 to π/2. So what I need is an angle that's negative coterminal to 11π/6, which would be what? If I were to go this way, -30, which is the same as negative, because it's got to be radians. -π/6. All right. This is the same as -π/6, and that would be my answer. All right. So that negative coterminal business, that could be weird, but when you really think about it, all you're doing is thinking about the reflection over the x-axis. So 11π/6 is a reflection over the x-axis of π/6. All right, so the same distance in the positive direction as π/6. All right, so just take the reflection and negate it, and you have the negative coterminal angle. So if I needed negative coterminal to 4π/3, take that, reflect it over the axis, negate that value. -2π/3 is the same as 4π/3. All right, navigating the unit circle is very important. All right, can you survive and get stuff right without really knowing the unit circle? Sure. Will you ever truly understand math? Probably not. Yeah. No offense. People only say no offense when they're about to say something offensive, which I think I just did. All right, so in the second one, the arc cosine of -√2/2, it's asking what angle has a cosine ratio of -√2/2 on the interval of 0 to pi, specifically 0 to pi. I'll put the question mark up here like I did the last one. All right, it's got to be the 0 to pi interval. If you give me anything else that's outside of that interval, it's incorrect. 3π/4, indeed. So we're looking for the x value. That's -√2/2. That corresponds to 3π/4. 3π/4 falls in the interval. So we're in good shape. Which is good, because sometimes it works out that way. As in, you could just pull it right off of the unit circle. You don't have to do anything else. But sometimes, you have to manipulate it a little bit. On the calculator, all right? So I quiz you on your knowledge of the unit circle, which is where you have to show me that you know these things. But on the test, you're allowed to use a calculator. So, there's kind of the marriage of the two ideas. So the question becomes, well, how can I get this off the calculator? On the test, you got to get stuff right? And so whether you know stuff in your head or not, it's not really the time for that during a test. All right. The problems after that are actually the bridge to differentiation related to this topic. So let's take 5, and then we'll go over these problems, and then we'll get into the derivative stuff. Pretty interesting.
running late.
No, it's cool. I got you for attendance. You're good.
Good stuff.
Yeah. You all right?
It's worse.
Dang.
Yeah, it's not.
How bad's the car?
Right bumpers. No. Great.
No.
Not
That
too
blows. What happened?
No, so I was going, it was 40 mile per hour speed limit, and yellow light comes, and this guy speeds up like he's gonna do it, so I speed up because I could easily make it too.
Right.
And he's like, at the last second, you know what? Screw it. I'm gonna slam on the brakes, and I'm like, oh no. Now I gotta stop. And then my ABS kicked in, and I didn't stop.
Yeah. Oh, that's rough. There's not nothing you can do.
There's nothing I can do, and I rear-ended someone's 30 on me. It's okay. It's gonna be okay.
When is our next test?
Thursday.
This Thursday? Okay. And also on the Unicircle test, I got a 7 out of 10. I'm not sure why.
Oh, I'll give him back in a little bit. Yeah.
Because I think I forgot what the it was pi over 3, pi over 4, and pi over 6. But then I forgot the rest. But I just added pi 30 degrees. So I might have not maybe I had 12 pi over 4, but I didn't or maybe it isn't This is an orange pen.
Yeah, I alphabetized it so it's right at the end.
Yeah.
You know what? I think they were just incorrect. Because that one
Are
should
you
have been
sure?
11 pi over. Oh, yeah. I do this
Oh.
for a living. So that one should have been 11 pi. Yeah, I think so. Yeah, this one should have been 4 pi over 3. This one should have been 2 pi. Well, that one you could have simplified. But this one should have been 4 pi over 3, so 8 pi over 6 maybe.
Wait. I just want to make sure. Pi over 6, 2 pi over 6, 3 pi over 6,
4 pi over 6, which simplifies to 2 pi over 3.
Okay.
5 pi over 6.
7 pi over 6.
6 pi over 6.
Oh,
6 over 6 is 1.
Okay,
7 pi over 6. 8 pi over 6.
Oh, that's wrong.
9, 10, 11. So that
I
got
can't
you.
get this half point for simplifying.
No.
Oh, okay.
Sorry.
That's okay. For this one, why did you choose cosine for V? Or does it matter?
It doesn't matter, but I always take the denominator because the denominator is more troublesome than the numerator.
Okay.
It's just a good strategy. All right, so let's continue on. Water bottle number 2. The sine of an arc function, so sine of an arc cosine or arc tangent or something like that. Now, you may look at part A, say, well, I'll just chuck that into my calculator, but then immediately see B and C and realize that that's not an effective strategy in all cases. And again, this is going to lead us to the concepts that we're going to tackle when it comes to finding derivatives and antiderivatives. So we're merging from pre-calc into calculus. All right. So what we're going to do is really just evaluate this arc cosine of 4/5. All right. So an arc cosine function, the result is always some angle theta. Right? It's some angle. Right? Now it's not always unit circle. Right? Because 4/5 is not one of our unit circle ratios. So what we're getting here is theta equal to the arc cosine of 4/5. All right, so you say, okay, well, what does that do? Well, an inverse of an inverse, well, that would be an ordinary function, the enemy of my enemy. So what I'm going to do is take the cosine of both sides of this function, or equation. So I'm just taking the cosine of both sides. All right, so on the left-hand side, it becomes cosine of theta. On the right-hand side, the cosine and the arc cosine are going to cancel each other out and leave you with just 4/5. All right, but it's still really not telling us anything we didn't already know. All right, until I consider that the cosine ratio is the adjacent side over the hypotenuse of a right triangle. All right, so I'm going to draw a right triangle, some arbitrary right triangle, with a reference angle theta. And I'm going to label the adjacent side as 4, the side adjacent to that reference angle theta. And the hypotenuse is going to be 5. And then I'm going to solve for the missing side. But fortunately, this is one of those nice situations. Yeah, it's going to be equal to 3. You could use the Pythagorean theorem, but it's a 3, 4, 5 right triangle. All right. So just going back to this, I called arc cosine of 4/5, I called that theta. So what this question is really asking me to figure out is, what is the sine of theta? So sine of theta is equal to the opposite side over the hypotenuse. The opposite side is 3. The hypotenuse is 5. So the result is 3/5. And since theta itself is equal to the arc cosine of 4/5, what we now know is that the sine of the arc sine of 4/5 would be equal to 3/5. All right. Again, a lot of work for something that could easily be popped into your calculator. But again, looking at B, no calculator. Well, that's not true. Plenty of calculators could help you with that. No calculator that you're allowed to use for this class is going to help you with that one. All right. So, but we also don't want to have to write out all this stuff every single time. So we'll see if we can streamline the process a little bit. All right. So since it's essentially the same question, just with, instead of theta being equal to arc cosine of 4/5, since theta is equal to arc cosine of x, I can kind of just jump right to this step here and say that if theta is equal to the arc cosine of x, that would mean that cosine of theta is equal to x. But I would just make the slight adjustment to that and say that x is really x over 1. Any number can be considered itself over 1. Like 5 is really 5 over 1. All right. It's still the adjacent over hypotenuse, so I'd have a reference angle theta with the adjacent side being x, the hypotenuse being equal to 1. I still need to solve for the missing side. Not quite as simple as 3, 4, 5. All right, so what I would do is just designate that as some missing side. I'll call it h for height, or we could call it b, a squared plus b squared equals c squared. You could designate it any way you want. So if I do it this way, it's x squared plus 1 squared, plus b squared is equal to 1 squared, in which case b squared would be equal to 1 minus x squared, with b being equal to the square root of 1 minus x squared. All right, just taking the square root of both sides. All right. Only positive, because we're talking about a geometric situation. We haven't converted this over the coordinate geometry. And even if we did, it would still be in the first quadrant, in which case this would be above the x-axis, so it's going to be positive anyway.
So when you did cosine of arc cosine x, that cancels out the arc cosine, right?
Yep.
Is that the same case for sine? Like
Sine of the arc sine? Yep. All right, so I now know what the missing side is here. And that tells me pretty much everything I need to know. So this is 1 minus x squared under the radical. The sine of theta, well, theta again is arc cosine of x. So I'm looking for the sine of the arc cosine of x is going to be the opposite side over the hypotenuse. So it just simplifies down to the square root of 1 minus x squared. All right. So it's like why? Why are we doing this? Yeah. Well, we know that this is moving into the realm of derivatives and antiderivatives. So I would ask you, do you know how to take the derivative of this? Maybe, maybe not. Right? It would involve chain rule because it's a function within a function. All right, so that's step one. The second part of it would be, do you know what the derivative of the arc cosine of x is? Well, if you studied that formula sheet, yeah. If not, no. All right? By using this process, we came up with an equivalent relation. And that is that the sine of the arc cosine of x is equal to the square root of 1 minus x squared. So if I ask you to find the derivative of this, you might say, no, I'm going to find the derivative of that, which is basic chain rule. All right, very easy to do, more difficult. All right, you still got to do some work, but this is algebra 1. All right, so if you have a choice in the matter, maybe you convert it over. All right, but again, if you know the rules, then it's all fine. But maybe you don't. If you don't, you have something to fall back on. All right. So part C is along the same lines, except it involves a tangent. Normally I'd throw a star on it, but I think it's different enough that it's worth looking at together. So theta is equal to the arctan of 3x. If I take the tangent of both sides, I get tan of theta is equal to just 3x. But again, just like the last one, I'm going to make that 3x over 1. All right. The tangent ratio is opposite over adjacent. So opposite 3x, adjacent 1. All right. So same idea, Pythagorean theorem. a squared plus b squared equals c squared. So 1 squared plus 3x squared is equal to c squared. So 1 plus 9x squared is equal to c squared, which means that c is really equal to the square root of 1 plus 9x squared. So I know my hypotenuse. So I have all three sides of the triangle. Now, just bear in mind, I mean, I'm just kind of going through a process here, and you might tailor that process to your own needs. I found the hypotenuse because it seemed like a logical thing to do, right? I have two sides of a triangle. Find the third side, right? But you think about why you needed to find that third side. In the last question, I was looking for the sine. Sine function is opposite over hypotenuse, all right? I had the hypotenuse, I didn't have the opposite. I needed that, I had to solve for it. Here, secant. Secant is hypotenuse over adjacent, it's reciprocal of cosine. I didn't have the hypotenuse, so I solved for it. But if this said find the, for example, cotangent. Cotangent is adjacent over opposite. You don't need the hypotenuse. If that were the case, my answer would be 1 over 3x and call it a day. You would never have to figure out the hypotenuse. So think about what ratio you need. In each of these cases, it turns out that you need, within the ratio that you're asked to find, the missing side of the triangle, but that's not always necessarily the case. All right, so secant of the arctan of 3x, hypotenuse over adjacent. So here's the hypotenuse, here's the adjacent, square root of 1 plus 9x squared. All right, and again, goes back to what I said in the last question. Would you rather find the derivative of secant of arctan of 3x or the square root of 1 plus 9x squared? Neither. Okay, I respect that. But the reality is the square root of 1 plus 9x squared, that's a Calc 1 question. Right? Anytime you can take a Calc 2 question and make it a Calc 1 question, you're probably moving in the right direction. That's probably something you want to be doing, right? So that formula sheet earlier in the packet that has all the rules, you just jot them down, and you got a little table here, you can fill them in, you can make flashcards, study them and everything. The purpose behind these questions is to learn the origin story behind them, because once you know what the formulas are, they're pretty easy to use. All right, so what we're looking to find is the derivative of the arc sine of u. All right, arc sine of u is some function y in terms of u. Really, this is just asking us to find dy dx. All right, but we know that the result of an arc function, so arc sine, arc cosine, whatever, it always gives an angle. So instead of saying dy dx, we might say instead d theta dx, with this being theta. All right, so this is an extension of what we were doing on the previous page, which is why we covered that, or reviewed that. All right, so if theta is equal to the arc sine of u, then what that means is that the sine of theta is equal to u. All right, when I'm finding the derivative, I usually like to have the lone variable by itself on the left-hand side. So I'm just going to make a slight adjustment here. U equals the sine of theta. Just switching it around, nothing big, nothing crazy there. All right, but now I want to find the derivative, because what we have here, we're looking for arc sine of u's derivative, so theta is equal to the arc sine of u is the same thing as u equals the sine of theta. So if I find the derivative of this, it's going to help me know the derivative of that. All right. So du d theta is equal to the cosine of theta. Now, it'd be nice if we were completely finished with the problem, but, you know, we need, again, this whole thing is the theta, right? We need d theta dx. That's not d theta dx. All right, so, well, I could make it so that it has a d theta on top. You do that. In a proportion, you flip one side. You can do that as long as you flip the other side. So I got a d theta du. All right, cool. Is equal to 1 over cosine of theta, which you might write as secant. I'm not gonna, but you could. Poor quality equal sign, so I'm gonna fix that right quick. All right, so we have a d theta du, we need d theta dx. All right, so I can do that. I need this to go away, so I'll multiply both sides by du. But I need to introduce a dx. So I'll divide both sides by dx. All right, this way the du's cancel on the left-hand side. And now I have a d theta over a dx, d theta dx. So we're good on the left. So that's great. The issue is I need a derivative in terms of x. That clearly says theta. So that's an issue. All right. But we have everything we need here to figure out what theta is equal to. All right. So we want it in terms of x, but we'll settle for u's. All right, because this really is chain rule. So there could be a u in there, there could be an x, there could be some combination of the two. The only thing that can't be there is a theta. That's got to go. All right, but I do have this relationship here. The sine of theta is equal to u. All right, and that goes back to the previous page. Sine of theta is equal to the opposite over the hypotenuse. Draw a little triangle here. Little theta action going on there. The u could be thought of as u over 1. The opposite side being u, the hypotenuse being equal to 1. So we would want to use the Pythagorean theorem to figure out what the missing side is, because I need cosine, which involves the adjacent side and the hypotenuse. All right, so I need that missing side, which would be what? Square root of 1 minus u squared, exactly. Okay, so cosine function, that part there is adjacent divided by hypotenuse. I have my adjacent, I have my hypotenuse. So that leads me to d theta dx is equal to 1 over the square root of 1 minus u squared times du dx. I didn't get it in terms of x's, but at least I got rid of the thetas. All right. Since theta is equal to the arc sine of u, that tells me that the arc sine of u dx is equal to this expression. All right. So 1 over the square root of 1 minus u squared times du dx. And that's the chain rule derivative for the arc sine function. All right, if you know a derivative, that goes a long way to help you figuring out antiderivatives. right? So if I'm given an integral that's in the form of 1 over the square root of 1 minus u squared, well, then I'm thinking that the antiderivative is going to involve arc sine in some capacity, right? So that's an important realization. But it comes from this process. All right, so I'll take you through another one, but you now have a rule that you can rely upon. Now, du dx, we could also write that as u prime. So another way to write this rule would be to say u prime over the square root of 1 minus u squared. Nice little byproduct of this is the fact that cofunctions for inverses, they're just negations of one another. So if you know sine, tangent, and secant, this is why I said last class, maybe 2 classes ago, that the most important trig functions aren't sine, cosine, and tangent. It's sine, secant, and tangent. All right? The ones without the cos. Because if you know the ones without the cos, then indirectly you know the ones with the cos. All right? Arc cosine has a derivative of negative u prime over the square root of 1 minus u squared. So same derivative, just negated. So negative poor quality prime. So negative u prime over the square root of 1 minus u squared. All right, so process-wise, nothing too crazy. I mean, it's just an extension of what we did on the previous page. But like I said, I'll take you through another one because, the first time through, nothing is as easy as I think it is. So this is my u. My theta. So theta is equal to the arctan of u, which means, by extension, if I take the tangent of both sides, tangent of theta is equal to u. And again, that's our trig function, opposite over adjacent. But to take the derivative, I want to write it as u equals tangent of theta. The derivative of tangent of theta is equal to what? Secant squared, in this case theta, normally x, but in this case theta. All right. Now again, ultimately I want d theta dx. I have du d theta. So I'm going to do my little flipping maneuver here. As long as it's in proportion. So fraction equal to a fraction, you can flip both sides. All right, so d theta du is equal to 1 over secant squared theta. So eventually I'm going to need to figure out what secant squared theta is. That's going to come from a triangle. So there's no way around it. You need a triangle. But before I do that, I want to manufacture that dx. So we multiply both sides by du dx. That cancels the du's and introduces the dx. But now we're going to start the mission to find the secant squared. So triangle. Opposite side would be u. Adjacent side would be 1. So what's my hypotenuse going to be? Square root of 1 plus u squared, exactly. All right. And I'll just show the extra step on this one because we actually have to square secant, so it makes sense to figure out what secant actually is first. Secant of theta is hypotenuse over adjacent. So in this case, it would be the square root of 1 plus u squared over 1, which is just the same as saying the square root of 1 plus u squared. So that's what secant is equal to. Secant of theta. I want secant squared. So I want that entire thing raised to the second power. So if I square both sides, so square the secant, square the radical. The radical is going to go away, right? You're just left with the 1 plus u squared. So we get our rule, which is that d theta dx is equal to 1 over, not the radical 1 plus u squared, just a 1 plus u squared times du dx. Which gives us a cleaner version of the rule. I'll just rewrite it above so you have a consistent place to look for things when studying. The cleaner version of that, again, du dx can be thought of as u prime. So write it as u prime over 1 plus u squared. All right? The arc cotangent is just the negation of that. Make that prime look primey. All right, so I'm going to put a star on the last one so you could try it on your own, but I'm also going to give you the rule so that you have something to actually work off of when you try the other problems that go along with it. It's u prime over the absolute value of u times the square root of u squared minus 1, and then the negation of that. At the very least, it's a paper saver. You know, when you're filling out, you're creating a note card, you should only have to write these three because you should know that these three are just a negation. All right? That's the idea of at least familiarizing yourself with the rules, not just relying on them being on a piece of paper. Procedurally, though, once you know the rules, this kind of questions are nothing. You just got to identify the u. Arc sine of u, arc sine of 2x. Ergo, 2x and u are the same thing. All right, so this is my u. So I'm just going to write a derivative that fits that idea. U prime 2 square root of 1 minus the u value, which is 2x squared. So 2 over the square root of 1 minus 4x squared. All right, so again, we're learning about derivatives in a course where the main theme is antiderivatives. Like, well, why is this the case? If you do enough derivatives, you start recognizing what a corresponding antiderivative is. So you do this problem. Now you look at this and you say, okay, if I see an integral that's in this form, I know what to look for in terms of its antiderivative. Had we done this problem prior to that one question where we had to manipulate it and come up with the arc sine function, if we had done this problem before that question, you look at this and say, oh, 16 minus x to the 6th power. All right, well, it kind of sort of has the same structure as an arc sine derivative. I wonder if that's an avenue I should pursue. You know, that's the kind of idea. The more experience you have with the derivatives, become more comfortable with the derivatives, the more likely you are to recognize it when an antiderivative kind of creeps along. All right. So the next two problems are just plugging and chugging and simplifying. So actually, yeah, the next two, but the one after that I'll take you through now. Because this is one of those pick your poison kind of things. You look at it and say, well, I can apply the chain rule or I could apply a strategy that I learned on the previous page. So I'll show you both ways just so you get a good handle on it. And then I'll let you decide which method you like more. Just understanding that sometimes you're kind of shoehorned into a particular approach. You don't really have a choice. Right? So let's say I wanted to use chain rule. We have an inner function, arc sine of 3x. So what I would do is take the derivative of my outer function. All right, cosine has a derivative that's equal to negative sine. All right, derivative. Not antiderivative. So if your first thought was, wait a minute, isn't it sine? You're in antiderivative mode, so you gotta go back and forth. Arc sine of 3x is my inner function, multiplied by the derivative of the arc sine of 3x. If you don't know the rule, this is not something you can do. All right, but we do know the rule, so we can do it. It's u prime over the square root of 1 minus u squared. So the u, that's this guy here, u prime would be 3 over the square root of 1 minus u squared. Again, 3x is the u. All right, little housekeeping. Sine of arc sine, they cancel out. So this whole piece here simplifies down to just a negative 3x. And the other part cleans up. All right, so just hanging on to the negative sign. The sine of the arc sine, those cancel out, leaving you with just a 3x, but then you still have to multiply it by the negative 1, that's the coefficient. All right. It won't work if, let's say, this were a tangent. If this were tangent of the arc sine of 3x, then you would have secant squared of arc sine. Secant squared does not cancel with arc sine. They have to be inverses of one another in order to cancel. All right, so this one actually surprisingly cleans up kind of nicely. Negative 9x over the square root of 1 minus 9x squared. Now, if you look at this, if I were to give you this problem as an integral, put an integration symbol in the dx after it, and they say find the antiderivative of this. You look at this with u substitution, you'd come up with the u of 1 minus 9x squared, and that would get you to an algebraic solution. You would never touch inverse or even ordinary trig functions in that approach. So what that means is that this is really just a disguised algebraic expression. So that's telling me that another approach is possible. The other approach is to say we have theta equal to the arc sine of 3x, which is the same as saying that the sine of theta is equal to 3x. Sine is opposite over hypotenuse. So 3x over 1. Now, I'm going to cheat a little bit here. I know the missing side has to be the square root of 1 minus 9x squared. I mean, I could figure it out in my head, not because I'm a genius. I mean, there's that, but also because I've done this problem like 1,000 times. But also, more importantly, most importantly, it's right there. It's going to work its way into our solution in some capacity. If there's going to be a radical in it, odds are it's going to be the square root of 1 minus 9x squared. So I skip that step. All right. So what I need is the cosine of that. I'll put my theta in there. Cosine is adjacent over hypotenuse. Here's my adjacent, here's my hypotenuse. So cosine of the arc sine of 3x is the same as the square root of 1 minus 9x squared. So instead of f of x being equal to the cosine of arc sine of 3x, I'm going to say f of x is equal to the square root of 1 minus 9x squared. If I put this function and the original function in my graphing calculator, it's going to give the same picture. It's going to give the same table of values. They are the same. They mean the same thing. the square root of 1 minus 9x squared is the same as 1 minus 9x squared to the 1/2 power. So when I'm looking for the first derivative, chain rule, 1/2, the inner function to the negative 1/2, 1 minus 9x squared, multiplied by the derivative of the inner function, negative 18x. Clean it up, and you know what it's going to end up giving you. All right, so one way or another, you get the same thing. And I would say that the level of difficulty is probably the same either way. Now here, it looks like you had to do, some fewer steps, I guess. But the drawback to this approach is if this came out to be anything other than sine, you got to go to a triangle anyway to simplify it. Otherwise, you have sine of arc sine of 3x as part of your solution, and that's, well, actually, it would be like secant squared of arc sine of 3x. You got to simplify that. It's got to be an algebraic expression, right? If it can be, it has to be, right? So you got to get rid of the trig and put it in algebraic form, right? So this technique, the alternate approach, which really ought to be your primary approach, is going to put it in algebraic form initially so that you can differentiate. All right, so, I mean, when I put it like that, hopefully I'm kind of steering you in the right